Assalamualaikum warahmatullahi wabarakatuh. We are from Group O, represent the heat exchanger project. So my name is Muhammad Anil Rosim, my team number is 20101 and I will present the introduction for our project. So what is a heat exchanger? Heat exchanger is a system used to transfer heat between two or more fluids, but there is no direct contact between them due to there being a solid wall surrounding them. One example of the heat exchanger is air conditioning. Heat exchanger comes in many varieties, and because of that, they are being categorized according to common characteristics. One of them is the direction of flow the two fluids have relative to each other. The three categories are counterflow, parallel flow, and cross flow. For this project, we only focus on counterflow and parallel flow. So for counterflow, it only exists when two fluids flow in the opposite directions. Because of the cooler fluid exists the counterflow heat exchanger at the same end as the hot fluid. The cooler fluid will reach the hot fluid's inlet temperature. Next, the parallel flow. So it only exists when two fluids flow in the same directions. The hottest cool fluid temperature is always lower than the coldest hot fluid temperature. So there are many types of heat exchanger that have been used in industry, such as flat heat exchanger, tube and shell heat exchanger, and etc. But the most used heat exchanger in industry is shell and tube heat exchanger, or we call it STHE, and we only use this type of heat exchanger in this project. So the major component of this type of heat exchanger is the tube box, shell, front and rear, and headers and baffles. The baffle supports the tubes, direct the fluid flow to the tubes in a natural way, and improve the turbulence of the shell fluids. The fluid pressure in the tubes is usually higher than the fluid pressure in the shell side. So this is an example of the component in the shell and tube heat exchanger. Next.
Hi, before I start my part, sorry, my name is Nisha Desai. My matrix number is 200-885. So today, my part is about the project design, which is the first design is about double pipe and counterflow, where the first design is in one tube and one shaft, where we have to reject this heat exchanger A because this type of heat exchanger is not suitable because it is the length of the heat exchanger is more than what the question asks, which is more than 2.5 after the calculation is made. And then basically this is not suitable because of the question. This is not suitable as what the requirement is asked. And then for the second design, we are using the multi-pass heat exchanger with parallel flow, tubes and one shell. And this also we have to have reject because this type of heat exchanger is more than what the question asks, which is more than 2.5 meter as well. So, and then for the third design, which is our final design, we choose that the multi-pass heat exchanger with counter flow, where two tubes and one shell, where this is one of the accepted heat exchanger because of the calculation also, where we have made it after this, we can see that this heat exchanger follow the requirements that the question asks, where it is less than 2.5 meters. And also there's some additional point that I would like to talk, where counter flow is more efficient rather than parallel flow, because inherently heat exchanger in counter flow are inherently more efficient than parallel flow as heat exchangers because they create more uniform temperature difference between the fluids over the entire length of the fluid path. So this is why we choose the design. also this is the 3D version design that I use AutoCAD, and this is the proof where this is the 40 tubes and one shell that what as question asked, and this one with the 3D version, and this is for the one tube and one shell. So lastly, we have made assumptions before we continue to the calculation part, where first design the first design in steady operating conditions as is the heat exchanger well insulated so that heat loss to the strongness and negligible and thus heat transfer from hot heat is equal to the heat transfer to the cold heat. The third changes in the kinetic and potential images of fluid streams are negligible. Number four, fluid properties are constant. And then for the second design, uh, there are same things like what in first design, which in 1 until 3 is the same, and there's some extra things which is for number 4 is there's no foley, and then the flow is fully developed, the properties are constant, the chamber resistance in the tube is negligible since the tube is small and highly conductive, and number 8, a heat exchanger with parallel flow. So basically the third design and third design is same, where the difference between them are actually heat exchanger for the second design in parallel flow, while the third design is in the counter flow. So we will continue for the next presentation, which is about the calculation. Thank you.
Hi, my name is Shara and my matrix number is 200459, and today I'll be explaining to you the calculation of a group. So first and foremost, we have to understand what the question required us to do, which is to design a heat exchanger with a length of tube pipe less than 2.5 meter. So it already gives us all the information that we wanted to do, and furthermore, we only have to assume what type of heat exchanger we're going to use. So yeah. This is the properties of the water at 25 Celsius, which will be used to calculate the velocity. And this is the information that we have collected from the question given. So first of all, you have to find the velocity and divide it by 40 because we want to focus for one pipe. And after that, we calculate the Reynolds number, the PR, because we want to know whether the fluid that flow inside the tube is turbulent or laminar. But here, the fluid that flow inside the tube is turbulent. Therefore, we use equation 868, and we obtain the Nusselt number is 71.679. And after that, we use equation 615, but because we wanted to find the inner heat coefficient. And we got that the answer is 2290. And because we already got the outer heat coefficient, we can actually calculate the overall heat coefficient. And before that, because we assume our tube is thin, therefore there is no R wall and no thickness involved. So the overall heat coefficient is 1297.55. After we calculate all of that, we determine the rate of heat transfer and also TH outlet. So to calculate the rate of heat transfer is by using mass of flow rate times with specific heat capacity and also change of temperature. So yeah, the TH outlet from all of that is 54.3 Celsius. Because we need to assume the type of heat exchanger we're going to use. So our final heat exchanger is exchanger C, which is a multi-pass that have one shell, two tube passes, and a counter flow. So first of all, you have to calculate the LMTD first, and we determine that it is 32.07 Celsius based on the temperature shown in the question. And yeah, because it is a multi-pass heat exchanger, we also need to find the correction factor because of the complex flow condition in the heat exchanger. So from value P and R, we found that in figure 1119, the correction factor is 0.95. With all of those information, we can now calculate the area of heat transfer by using equation 1124, which can be found by Chengal in the textbook of Chengal. So the area is 10.57. And we also assume that our heat exchanger has two tube passes, therefore we divide it by 2 and we obtain the actual area. And yeah, before that, we wanted to find the length actually, therefore we divided by this area of the area of the pipe and also the number of tube, which is 40, which already have been stated in the question, 40 tube. And the answer that we have obtained is 2.214, which is an ideal heat exchanger, and also fulfill the requirement the question have asked us, which the length of tube must be less than 2.5 meter. So that's all from question A. Moving on to question B, which is we are required to find the magnitude of following factor on our chosen heat exchanger. So, our heat exchanger is heat exchanger C. And first of all, you need to find the new rate of heat transfer, TH outlet, and also T LMTD and mu. So the question stated that the TC inlet less decreased by 3 Celsius, therefore we minus it by 3, and the new TC outlet is 42 Celsius. And from all of the working method, the new U is 976.433. And with this, we applied it to equation 11.8, and the new magnitude following factor based on our heat exchanger is 2.535 times 10 to the negative 4. And that is all for question B. So to see the overall result, I've already put it in this tab in this table. So there are 3 types of heat exchanger, and this is all the length of the pipe from each of the exchanger and also the falling factor. So that is all for calculation. Thank you very much.
My name is Raja Aisyah Malisa binti Raja Balisha. So now I will continue for the discussion of our mini project. So we use a fluid characteristic of temperature 25 degrees Celsius from table A9 as temperature reference for this shell and tube heat exchanger. So from the table, we get the density 997 kg per meter cube. The heat capacity is 4,180 joule per kilogram Kelvin. The dynamic viscosity is 0.891 times 10 to the power of negative 3 kg per meter second, and the Prandtl number is 6.14. So the length of the tube heat exchanger must be below 2.5 meter as stated based on the question because of the space limitation. So for the assumption, we assume the designated tube heat exchanger is thin, hence the area can be neglected. So dO is equal to dI and the R wall is also neglected. So the kinetic and potential energy are negligible, hence we will have a steady operation. So the fluid properties are constant. So the first design that we suggest is a double pipe counterflow design. So based on the calculation, we get the L value is 4.21 meter, and this design is rejected because it does not satisfy the space constraint, which is the length is more than 2.5 meter. So the second design is a multi-pass 1 shell and 2 tube pass with a parallel flow. So in this design, we need to calculate the P value and R value to obtain the F value. So the F value that we obtain from figure 11.198 is 0.95. So at the end of the calculation, we get the L value is 2.76 meter. And this design is also rejected because it does not follow the space limitation. So the third design that we suggest is a multi-pass 1 shell and 2 tube pass with a counterflow. Similar calculation has been done, and at the end of the calculation, the L value is 2.214 meter, and this design achieves the desired length tube as it follows the limit length tube of the heat exchanger, which is below than 2.5 meter as stated based on the question. So why we choose multi-pass, 1 shell and 2 tube pass with counterflow? So for counterflow, the arrangement typically exhibit the highest efficiency as it allows for the greatest amount of heat transference between fluid and consequently the greatest change in temperature. It also provides a more constant temperature difference between the fluid over the whole length of the fluid route. For the parallel flow, although this layout provides the most thermal homogeneity throughout the heat exchanger wall, it often has lower efficiency than a counter flow arrangement. So why we choose multipass instead of double pipe? This is because by using a multipass tube offer great flexibility for optimizing fluid velocity, pressure drop, and heat transfer. When there are two or more pass inside the exchanger, the available space for each pass is limited. So the flow speed increase and more heat exchange is generated. So in other words, the primary rationale for having more tube pass is to increase the surface area. Heat movement within the heat exchanger will be quicker. In comparison to employing fewer tube, the process will be more efficient and faster. So using more than one tube pass will aid in heat transfer to the maximum in the shortest amount of time. So that's all. Thank you.
So, for the conclusion, we can conclude that heat exchanger C is the most preferred heat exchanger than A and B. The characteristics of heat exchanger C are multipass with counterflow heat exchanger, which is of the three types of heat exchangers. Counterflow heat exchangers are the most efficient than parallel flow because they provide a more constant temperature difference between the fluids over the whole length of the fluid routes. In contrast to the parallel flow heat exchanger, the counterflow heat exchanger can allow the cold fluid to exit with a higher temperature than the exiting hot fluid. To add, we use a multipass heat exchanger because it can save a lot of space. When using a multipass heat exchanger, fluids may go to the end of a unit and then return maybe for numerous times. Thus, it can reduce the tube length of the heat exchanger. So that's all from us. Thank you.